Hello students, in this session I will discuss some of the chemical reactions which are from very most well-known organic chemistry book that is written by Jonathan Clayden, Nick Greaves and Stuart Warren. Okay, this is one of the most important book, and in this one every chapter is explained in detail, and it's very colorful book. All of you know, I think organic chemistry lovers, most of you know about this book. Okay, so for every competitive examination, either IIT-JEE advanced or GATE or JAM or CSR exam or civils exams, so whatever the exams, this is the most useful number one book. Okay, so I would like to discuss some important topics from this most important book, that is Clayden, Greaves, Warren, Water. So here first of all, one of the most important topic, that is a chemoselectivity and protecting groups. So what is the chemoselectivity first of all? So of course that means here this chapter involves most of the uh, reduction reactions. So here this is the 23rd chapter in this textbook. So here first of all, that what is the chemoselectivity? Chemoselectivity, that means the some uh, uh, terms are there in organic chemistry, that is chemoselectivity, stereoselectivity and rheoselectivity. So like that, some terms are there. So first of all, here let us try to discuss about the chemoselectivity. So what is the chemoselectivity? Which function group will react with the added reagent? Okay, which functional group will react with the added reagent? For suppose here, let us discuss with this simple example. All of you know this about the acylation reaction of alcohols and amines. So generally here, simple reaction, this is alcohol, this one on reaction with the acetic anhydride, that H replaced by the acyl group. Okay, first here removal of the acetic acid, so H replaced by the acyl group, that is nothing but acylation reaction. Okay, now here, and similarly that amine also involved in acylation reaction, that amine on treating with acetic anhydride, so we'll get this same product. That means here that H replaced by the acyl group, that is nothing but N acylation here, C double bond O CH3. Okay, it is the acylation reaction, that H replaced by the acetyl group. This is okay. So now in this case, here generally that this compound contains two OH, that means two functional groups, OH and NH2. So actually here that OH acting as a nucleophile and NH2 also acting as a nucleophile. So in this case, so with excess of the acetic anhydride at 100 degrees centigrade, both the hydrogens of the OH and the hydrogen of the NH2 will replaced by the acetyl group. Okay, that means here OC double bond OCH3, and next here NHC double bond OCH3. Okay, when excess of the acetic anhydride is added. So in this case, on both functional groups here reaction takes place. But whenever we will take this acetic anhydride in one equivalent. So one equivalent means here that either OH or NH2. That means here this hydrogen or this hydrogen replaced by the acetyl group. So actually here first of all, the based on the mechanism we can explain this reaction. So here first of all, this is acting as nucleophile. That alcohol acting as nucleophile. This nucleophile attacks on this carbonyl carbon. Okay, that means here the electrons are transferred to this one. So here first this reaction involves a nucleophile attacking on the acetic anhydride. Okay, and then here reformation of pi bond and leaving of this group takes place. Finally that hydrogen replaced by the acetyl group. So I hope all of you know this mechanism. Okay, so this reaction involves a nucleophile attacking. So here whenever we take one equivalent of the acetic anhydride, so here between these two, which is a more reactive, so that NH2 is a more reactive. That means here that NH2 is a strong nucleophile, that is a less electronegative. It is a good electron donor when compared to non-bonding electrons on the oxygen. Okay, that oxygen is the most electronegative element than the nitrogen, so that oxygen holds electrons very tightly, so it is a less nucleophilic when compared to NH2. So whenever if you take one equivalent of the acetic anhydride, that hydrogen of the NH2 replaced by the acetyl group, so we will get the this compound NHC double bond O CH3. Okay, and we can say this is the chemoselective reaction. Chemoselective reaction. Okay, that means here that between OH and NH2, especially that one functional group involved in a reaction, okay, with the acetic anhydride, it is a chemoselective reaction. That means here in a chemical reaction, selectively one functional group is involved. Here in this case, in this chemical reaction, no selectivity, because here that OH and NH2 both functional groups are involved in a reaction, so it is a not chemoselective. This is a chemoselective reaction. Okay, and you know that this is a paracetamol. Okay, this is a paracetamol, and its name is para-hydroxyacetonilide. Para-hydroxyacetonilide. Okay, and next this compound. This compound contains ester, and this compound contains amide. So this one on hydrolysis. So actually here the controlled hydrolysis here, controlled hydrolysis of this compound, so produce paracetamol, that means NHC double bond OCH. Why? Because that means this is involves a hydrolysis actually. So here between ester and amide molecule, which is more reactive in a hydrolysis process, ester is a more reactive. Okay, so here in this case here, this NH is a strong donating group that donates electrons to this carbonyl group. Okay, it means here that magnitude of the positive charge at this carbon decreases, but in this case here that oxygen is a weak donating group when compared to NH. So here in this case here that magnitude of the positive charge at this carbon is more. That's why here hydrolysis takes place. It is a more reactive. So first of all, that ester is hydrolyzed than the amide. Okay, so that is the first one. So next, so one more reaction. Okay, so all these reactions from the organic chemistry book, that is a clayden. So here in this case, one equivalent of the this lithium compound, that means that is the alkyl lithium. So its structure is HC triple bond C minus Li plus. Okay, that means it is a like a organometallic compound. It is like RMGX. It is also involved in a addition reactions like Grignard reactions. So here between ketone and ester, this compound contains two functional group, but here especially when you take one equivalent of this organometallic compound, that more reactive functional group is attacked by this organometallic compound. So between ketone and ester, the towards which is more reactive, that means here the ester is the less reactive, because here this one is acting as a plus M group, so that decrease the magnitude of the positive charge. Here the more positive charge, then it is readily attacked by this nucleophile. Here in this case, this is a plus M effect, so magnitude of the positive charge at this carbon decreases. But in this case here, there is just here methyl group. This methyl group is a plus I group. Okay, so that means it is a weak donating group when compared to OCH3. So here this nucleophile majorly attacks on this ketone. So the product is followed by hydrolysis. Let us consider that followed by hydrolysis. That means here, for suppose O minus Li plus, here nucleophile is C triple bond C, and then here C double bond O OMe. Okay, so followed by quenching with water. So we'll get this C triple bond CH and double bond O Me, here in this case OH. It is a chemoselective reaction, because here the selectively ketone functional group is attacked by the nucleophile but not ester. So here I like to remember that remind the reactivity of the different compounds towards nucleophile. So acidic halides are more reactive than the aldehydes and ketones. Next here, anhydrides, ester, amides, and this carboxylate anion is a very less reactive, because that is a O minus is a very strong donating group. That strong donating group decrease the magnitude of the positive charge at this carbon. So whenever there is a very less magnitude of the positive charge at this carbon, that is less attacked by the nucleophile. There is no tendency to attack a nucleophile on this carbon because there is a less magnitude of the positive charge. But in this case, the minus I group, that Cl is the minus I group, that minus I group increases some magnitude of the positive charge. So higher the magnitude of the positive charge, that nucleophile readily attacks on this electrophilic site. So based on the electronic effects, this is the order. I think you can understand this order. Okay. So the based on the electronic effects, here hydrogen, nothing, here alkyl plus I effect, here this one plus M effect, this one also plus M effect, this one also plus M effect. But here it is a weak plus M group when compared to this alkoxy group and NH2 group. So yeah, the stronger the plus M effect, very less magnitude of the positive charge, then it is less chance to attack by the nucleophile. Okay. So next, and now how to reduce aldehydes and ketones to alcohols. So actually you know that the ketones on reaction sodium borohydride, that ketone is reduced to alcohol. So here in this case, that it is a Na plus and BH4 minus, that H minus from the BH4 minus attacks on this electrophilic carbon. The transfer of electrons takes place to the oxygen. This O minus accepts the H plus from the solvent here. So finally we will get this compound. So here in this case, again here addition that side product is E2O and BH3. That means BH3 minus. Here still there are the 3 hydrogens. So here that it can reduce furtherly 3 moles of the aldehyde or ketone. That means here the 4 moles of aldehyde or ketone reduced by the 1 equivalent of the sodium borohydride. That means 1 mole of the sodium borohydride. Here 4 moles of the alcohol we will get. Here H and all. Okay. So here in this case, esters to alcohol. So esters can be reduced to alcohols by using lithium aluminum hydride. This lithium aluminum hydride is a strong reducing agent than the sodium borohydride. So here product is CH2OH, and here in this case R-OH. Okay. Here in this case, the sodium borohydride no reaction. Sodium borohydride is less reactive when compared to lithium aluminum hydride that cannot reduce the esters. Okay. Now here lithium borohydride slightly more reactive than the sodium borohydride, so it can reduce esters also. The products are same as in the case of lithium aluminum hydride. Okay, so here you can say reactivity order of these reducing agent. Lithium aluminum hydride higher than the as lithium borohydride, and next sodium borohydride. The sodium borohydride is a weak reducing agent. Okay, and lithium aluminum hydride is a strong reducing agent. Between these two here, lithium borohydride reactivity. So generally you know that the mechanism of the lithium aluminum hydride with ester. So here first of all this ester attacked by the H minus, so we'll get this intermediate compound. This intermediate is unstable because this carbon attached to the 2 oxygens with a single bond. So loss of this one, and you will get the aldehyde. Again this aldehyde attacked by the H minus from the lithium aluminum hydride. So we'll get the intermediate. So this one on hydrolysis will get the alcohol. Okay, so here in this case 2 hydrogens are involved in a reaction, that means to reduce ester into alcohol. So here totally you can see here the balancing reaction, that is ester. The 2 moles of ester is reduced by the 1 mole of the lithium aluminum hydride. It is totally the balanced equation for the ester reduction. Okay, so next yeah, so you know the reactivity of the sodium borohydride, lithium aluminum hydride, and lithium borohydride. So here it is ester and ketone. The sodium borohydride ester is not reduced and ketone is reduced. So here in this case we can see it is a chemoselective reaction. Okay, and next lithium aluminum hydride, that can reduce of both. So it is a non-chemoselective reaction. Ester is converted to alcohol and ketone is also converted to alcohol. Now lithium borohydride, the lithium borohydride can reduce the esters as well as the ketones. The products are the same. Okay, so now here the reduction of the esters in the presence of the carboxylic acids. So lithium borohydride can reduce the esters but not acids actually. Okay, so here the lithium borohydride, the important point is that can reduce aldehydes, and that can reduce ketones, and that can reduce acid halides, and that can reduce esters only. Okay, so but not remaining compounds, that means carboxylic acids are not reduced and amides are not reduced by the lithium borohydride. So here in this case, lithium borohydride selectively reduce the ester in the presence of the carboxylic acid. The carboxylic acid are not reduced, so carboxylic acids remains unaffected. So product is this one, methyl alcohol. So it is a chemoselective reaction because that selectively lithium borohydride attacks on the ester functional group. Okay, that's it. And next here, that one more reaction, that how to reduce amides to amines by using lithium aluminum hydride, that amides can be reduced to amines. Okay, so in this case these two hydrogens from this lithium aluminum hydride. So actually here in this case you can see the mechanism of this reaction. So here by directly I can show from the textbook here. So this is the mechanism of the reaction, that amides to amines. So first of all, that lithium monohydrate, that H donates to the, that means attacks on the alkophilic carbon. So we'll get the this tetrahedral reaction intermediate. So from this tetrahedral reaction intermediate, we will get this imine actually. That tetrahedral reaction intermediate unstable. So here we'll get the imine. So loss of this aluminum oxide with the hydrogens also. So here in this case, finally, that imine also can be attacked by the H minus. So this imine reaction is almost similar to the carbonyl compounds. So by transfer of these electrons, that the carbon plus attacked by the H minus, so we'll get the NO2. So it is a completely different. So here the amides are not reduced to the alcohol, that amides are reduced to the amines in this case. Okay, these two hydrogens from the lithium aluminum hydride. So that is the mechanism of that reaction. So you can see here in this case, for cyclic amides, C double bond O, here in this case CH3. So lithium aluminum hydride. So for suppose that CO converted to CH2 and NCH3, that means here amide is converted to amine. Okay, this is one of the most important point. For suppose here these amides are not reduced by the sodium borohydride, NaBH4. Okay, that means here for suppose here there is a ketone functional group and there is a amide functional group. So by reacting with sodium borohydride, in this case this ketone is only reduced but not amide. That means here we can say it is a chemoselective reaction, double bond over NH2. That's it. And next one more reaction, that is the carboxylic acids to alcohols. Okay, so this the carboxylic acids to alcohol, this conversion we will continue in next video. Thank you for watching. Please subscribe my channel for more videos.